Following on from David's lectures earlier this morning, I'm going to talk about detection attribution. So the outline of the talk is, firstly I'm going to explain why we're interested in attribution in the first place, and then I'm going to talk about both trend and event attribution. So trend attribution being about finding statistical change in a variable, a trend, and attributing that trend to a particular forcing. And then event attribution being about a specific extreme weather or climate event and attributing that to a particular forcing. I'm going to talk about where attribution is going and what's next. So why do we do attribution in the first place? Well, it's useful to understand the causes of trends, not just identifying changes in the climate system, but understanding what's driving those changes. And we can make useful statements, quantitative statements, based on attempting to attribute those trends or those extremes to a particular cause. And we're not interested in caused climate change, but also in various different aspects of natural variability. So whether that's things like the El Nino Southern Oscillation, or volcanic forcings, solar forcings. And we can also try and separate individual influences. So we can look at, for example, the anthropogenic influence through greenhouse gases only, versus anthropogenic aerosol emissions. And another reason for doing it is a less scientific-based reason, is that it's quite a good communication tool. As long as it's framed well and well communicated in general. So there have been occasions where attribution studies haven't been communicated very well and have caused confusion. If they're framed well and the journalists who are writing or speaking about the study understand quite well what's been done, they can be quite an effective communication tool. Firstly, talking about trend attribution, more of the talk's about attribution, but I thought I should talk about trend attribution first. Here is about understanding how much different forcings, so whether that's things like emissions, anthropogenic aerosols, volcanic forcings, how much those contribute to observed trends in the climate system. Whether that's temperatures like on the graph I'm showing there, or regional temperatures, or precipitation, or some other variable. A trend in the climate system we can detect, but detection alone doesn't explain the cause of the trend. So detection is just a statistical problem, identifying a change in the climate system. We need attribution to attempt to understand the cause of the trend and identify what's the most plausible cause for a change in that particular variable. So, as a good example is that global temperatures, by any kind of statistical measure we use, we can detect a change. There's lots of different ways you can use statistically finding change in global average temperatures, whether that's comparing global temperatures. I don't know if you can see the pointer I'm using. If we're looking at global temperatures at this end of the distribution, at this end of the distribution, we can see that they're different. We can see that it's a trend. So we can then use models to formally attribute the change to various different forcings. It didn't come out particularly well, but it shows from a recent paper by Peter Stott. On the left, we've got the global average temperature anomaly as the black line, and the various orange lines are climate model simulations with natural and anthropogenic forcings. And you can see the grey bars show individual volcanic eruptions, like Agung here, Pinatubo here, and you can see the effects. You can see that they're in the climate model simulations because there's a dip after them in the global average temperature. And what we can see is that when we include both natural and anthropogenic forcings in our climate model simulations, we can reproduce the trend fairly well. But on the right, if we take out the anthropogenic forcings, as shown by the individual blue lines in the different climate model simulations, we can see a clear separation towards the end of the series. So the natural forcings alone don't explain the trend we see in global average temperatures. Obviously, the red and thick blue lines on these graphs are the ensemble means, so they have reduced variability compared to simulations and the observed global temperature. So clearly, if we take out the human influences, we do not capture the observed trend. And we can look at this as well for different regions of the world, and also for things like content in different basins. And here on these graphs, the black line is the observed series, and the kind of pinkish bars are the all forcings world, so that's natural forcings and anthropogenic forcings, and the blue lines are taking out those human forcings. And we can see this clear separation in many regions. We can't explain recent trends, recent changes in the climate system when we take out the anthropogenic forcings. So by doing trend attribution analyses, this allows statements to be made about global and regional series and ocean heat content. Like this one, saying that it's extremely likely that more than half of the observed increase in average surface temperature from 1951 to 2010 was caused by the anthropogenic increase in greenhouse gas concentrations and other anthropogenic forces together. So by doing these attribution analyses, we're able to make these statements. And this goes well with one of the other major statements from the IPCC AR5 report, saying that warming since the mid-20th century has been unequivocal. So there's definitely been warming of the climate system. This then goes to explain the cause of that warming. We also make statements, regionally based statements. So this is also in the IPCC summary for policymakers from the 5th assessment report. Over every continental region, except Antarctica, anthropogenic forcings have likely made a substantial contribution to surface temperature increases since the mid-20th century. So how do we actually do trend attribution? One of the main methods is differencing. So this is a multiple linear regression model where we take different forcings and we scale them and add them together to try and reproduce the observed series, whether it's global temperature, regional temperature. And by doing this, we find that you need those anthropogenic forcings, those greenhouse gas concentrations in our models to explain. So now I'm going to move to event attribution, and this will be the main part of the talk. This is kind of a newer field of attribution. So trend attribution has been around for quite a while now. Event attribution has only been around the last 15 years or so. And it uses slightly different techniques, but the same kind of basis of observations and models with different forcings. It's trying to answer in how has event X changed due to forcing Y. And the idea is to try and make a quantitative statement based for a particular event. It's usually focused on the roles of anthropogenic climate change, various different major modes of natural climate variability. So trend attribution is often focused on things like oceanic forcing or solar variability, whereas event attribution, because we're looking at a snapshot in time as opposed to an overall time series, we're more interested in what's going on in the climate at the time. So there's less emphasis on things like solar variability and volcanic forcings, and more emphasis on internal modes of variabilities. So things like the El Niño Southern Oscillation, the Indian Ocean Dipole, North Atlantic Oscillation, if we're interested in a European extreme, for example. And usually we're interested in how these influences alter the frequency of a particular type of event or the intensity. So we're looking at a class of event associated with a particular extreme. So for example, if we were interested in a heat wave, we'd look at other heat waves and look at how the frequency of that type of heat event, or the intensity of type of heat event has changed, either due to anthropogenic climate change or due to natural climate variability. This is done using model simulations, and basically we normally compare two ensembles of model simulations if we're interested in the role of anthropogenic climate change. We have a model ensemble containing lots of simulations representing climate here, and lots of simulations representing the climate of today, and we can make comparisons between those. And we use those model ensembles to form distribution, representing our world of today. So this is from the same paper by Peter Stott I was showing you before. World of today being the red distribution here, a counterfactual world without anthropogenic forcings being the green distribution. So for a particular climate variable, we construct these PDFs, and we look at the change in likelihood of a particular extreme event exceeding a certain threshold. So, for example, if this was a temperature distribution and we were looking at something exceeding, say, the 90th percentile on a natural world, and it was, maybe the 70th percentile in the world of today, then we would say it's about 3 times more likely this kind of heat extreme due to anthropogenic climate change. So that's the basic idea. But before we do any kind of event attribution analysis, there's quite a lot of different things to consider. And we basically need all these different ingredients to come together before able to do any kind of analysis. Firstly, and fairly obviously, we need an extreme weather or climate event. We need something in the tail of the distribution. If it's, if we're looking at an average temperature, then it's not a very interesting event to look at. So we need something extreme. Often we look at record-breaking events, so something outside historical, unprecedented in the historical record. So there have been lots of different event attribution studies for various different types of extremes, a few in Australia. This is just an example of hot and cold seasonal extremes. So Sophie Lewis led a paper in 2013 with David Caroli looking at the angry summer of 2012-2013. So that was Australia's record hot summer, and she finds that anthropogenic climate change made that event at least 2.5 times more likely. There have been also attribution studies for cold extremes, including one for frost days in Western Australia. Also, in terms of short timescale extremes, there have been a lot of studies looking at heat waves and cold spells, including a study led by Sarah Perkins-Kirkpatrick in 2014, looking at heat waves during the angry summer and the anthropogenic contribution to those. There have been studies looking at heavy rain events. Heavy rain events are a bit harder to look at because, I mean, eventually attribution is like a signal to noise problem. And rain events, the signal, the trend is smaller variability or noise. So it's harder to identify the change as clearly. And there have been lots of other different studies on droughts as well, blocking high pressure patterns as well. But also recently there's been a focus looking at tropical cyclones, and this has kind of been triggered by the fact that in the North Atlantic last year there were quite a lot of devastating tropical cyclones across the US and the Caribbean. Hurricane Harvey alone, which I'm sure many of you remember that tropical cyclone because it caused a lot of flooding in Houston, in Texas particularly. There's been a lot of study in the US of that event and the role of anthropogenic climate change to do with different variables relevant to tropical cyclones, including the ocean heat contents in the lead up to the event and the precipitation that was produced by the tropical cyclone. So we need, firstly, our first ingredient is that extreme weather event or extreme climate event. Our second ingredient, which is occasionally overlooked, is the fact that we need a really good observational data set we can trust. But this isn't as easy as it first sounds, because for a lot of the world, we don't really have very good observations, and that means that we can't get an extreme event in the context of the historical past as easily. So this is just a figure from Marcus's paper, just showing locations of stations around the world, the temperature or daily temperature extremes on the top, the heavy rainfall days on the bottom. And you can see that there's good concentrations of data in North America, Western Europe, in Eastern Asia, and for much of Australia and New Zealand as well, although there is a bit of a gap in Central Australia. So these regions, we can do attribution studies for these kinds of variables, but for many parts of the world, unfortunately the parts of the world where climate change enhanced extreme events are likely causing more devastation. So in sub-Saharan Africa, in parts of South America, we just don't have the observations to the confidence in, firstly, the event being an extreme event, and then having good observations that we can use to evaluate our climate models that we use for these studies. So this poses a big challenge, and there's different ways that you can kind of approach this, because we still want to do event attribution studies in these developing parts of the world. So we can do kind of data set comparisons using lots of different observational data sets, for example, and including reanalyses. But sometimes it's not possible to do an event attribution study just because we can't contextualize that extreme event in terms of the historical past. And I've shown you here the locations of stations for where temperature and precipitation are observed. But if we look at other variables that we might be interested in, like soil moisture, if we are interested in droughts, for example, the observations become much sparser. So it's definitely a challenge if we're looking beyond things like temperature, precipitation, or mean sea level pressure, it becomes a lot harder. Another ingredient we need is a good understanding already of how climate change and climate variability affect a particular variable. So we know, for example, in Australia, that we have, I'm sure most of you have seen this figure quite a few times before from James Risby's paper. We have lots of different modes of climate variability affecting the Australian climate system, including the El Niño Southern Oscillation and the Indian Ocean dipole. So we need, it's useful to have a understanding of how these different climate modes affect extreme weather events that we're interested in before we start doing our attribution study. Otherwise, we would struggle to contextualize the results or make sense of the model results that we might get at the end. And one of the challenges here is that there aren't that many studies that look at the links between these different climate modes and extreme weather. There have been a couple of studies. So for example, Sarah Perkins Kirkpatrick led a study looking at drivers of heat waves in Australia, looking at ENSO, Southern Annular Mode, Indian Ocean Dipole. And I've done a similar study looking at extreme rainfall drivers. But in order to look at more unusual extreme events, we would really want that basis of knowing how different climate modes in the past have affected those types of extreme. The other thing we need, of course, for event attribution is the right climate model simulations. So we have to know that the climate model setup we want to use is right for the job. There's lots of different types of climate models. So for example, if we were interested in something like a tropical cyclone, a type of extreme weather which we know is strongly linked with atmosphere-ocean coupling, we know that when we have a tropical cyclone of the ocean, it mixes together the surface water and brings cooler water to the surface. If we were looking at an atmosphere-only model, looking at that type of extreme weather event with prescribed sea surface temperatures, that probably wouldn't be a good idea because that model would miss the fact that that mixing was occurring in the surface layer of the ocean. Similarly, if we were looking at a highly localized extreme event, say an extreme temperature event in Sydney, where I'd only be in because the topography is quite complex around that location, we probably would want to use a coarse resolution global climate model. We'd want to use something much finer scale than, say, a CMIT-5 climate model. So the picture in the bottom right is actually taken from running the weather at home model, which is an atmosphere-only model setup, which is a finer resolution than a coupled or climate model, but also has its limitations as well. So this is a very important consideration when designing an event attribution study. And the other thing, of course, is we need climate model simulations that we can trust. So there's no point if the climate models have really big biases or they're not doing a very good job of capturing teleconnections, then we probably shouldn't be using them to do an study. So the questions we want to ask ourselves are, do the models capture observed trends in the first place? We obviously allow some leeway because if we were interested in using coupled global climate models, we can expect them to capture trends perfectly because internal variability in those models is different from in the real world or occurs at different times. But we would still expect those models to capture the general sense of the trend. We'd also hope that the model capture observed variability as well. If a model has too much climate variability for a particular variable, then it might skew the attribution result, because on those distributions we're looking at, that distribution might just be too wide, for example. And we also want that the models capture the relevant teleconnections. If we're looking at, for example, rainfall extremes in the Murray-Darling Basin in Australia, there's a very strong ENSO teleconnection to summer rainfall in that region. If we're using a model that just doesn't have that teleconnection, we wouldn't have too much trust in its ability to. If the models fail to do even one of those things very well...
Hi, Andrew. Sorry, can you repeat the last point? The sound dropped out as you said we wouldn't trust in its ability to.
I think, so I don't know if you caught the bit I was explaining about teleconnections. So we would want models to capture teleconnections. I used the example of the Murray-Darling Basin rainfall, which we know in the real world is strongly linked to the El Niño Southern Oscillation. If our models don't capture that very well, then we would run into problems. And the point I'm making here is that if the models fail to do even one of those things very well, then we're going to have an attribution result that we wouldn't necessarily trust. Cool. So we have all of these ingredients that we have to have come together before we can really do an attribution analysis that we can rely or have some confidence in the result that we would get. So I'm just going to show you an example analysis looking at the record wet winter we had in Southeast Australia in 2016. And through all of these ingredients before producing the attribution statements at the end, I made sure it was an extreme event. We're quite fortunate in Australia that we have good observations to base our attribution studies on. In this particular study, I used the AWAP gridded data set of rainfall. And over Southeast Australia, there's a fairly dense observational network. For Southeast Australia, there have been lots of studies looking at how climate change and climate variability affect extreme rainfall in Southeast Australia. And I tested different climate model simulations, as I'll explain in a minute. So for this event, it was an extreme event. It was the wettest July to September on record. So that's how I'm defining winter in this. In this event in 2016, if you were in Melbourne or Canberra, you probably, or Hobart, you probably remember this winter because it was very wet. We had frequent frontal systems crossing the region, and the event culminated in the Adelaide blackout storm. So this is the statewide South Australia blackouts at the end of September that caused so much political furor afterwards. The event itself coincided with a record negative Indian Ocean dipole, which we know has teleconnection with Southeast Australia wintertime rainfall. So this is just on the left, we've just got a picture from the Bureau of Meteorology showing negative Indian Ocean dipole patterns, so warmer sea surface temperatures in the East Indian Ocean cause more convection, and through Rossby wave train you get an increased chance of rainfall in Southeast Australia. And if we look at the SST anomalies for the East Indian Ocean on its own, so it's a bit different from the dipole, just taking the East Indian Ocean, we see that 2016 was the second warmest on record. And you can see an overall trend towards warmer East Indian Ocean SSTs related to climate change. That's previously been attributed to climate change. If we look at precipitation during July, August, September in Southeast Australia, we don't really see much trend. we see that 2016 was the wettest July to September on record, but overall there's very little of a trend. I should say these anomalies as a percentage from the 1961 to 1990 climatology. So in 2016 it was about 50% wetter than normal. So for this study, I used CMIP5 models, and I evaluated them for their rainfall variability and trends in Southeast Australia, and also that teleconnection with the East Indian Ocean sea surface temperatures. We know that this was a particularly relevant climate mode for this event, so we wanted to make sure that the teleconnection was captured properly. I used these models then to examine the role of both human-caused climate change and natural variability related to the warm Indian Ocean sea surface temperatures for this particular event. And because I'm interested in only the natural variability, I detrended the sea surface temperatures as well. So if we construct distributions a bit like that idealized figure I showed earlier in the talk from Peter Stott, this is just showing on the x-axis is just the Southeast Australia winter rainfall anomaly as a percentage, and this is a PDF. The blue curve, the blue histogram, which is kind of hidden behind the other histograms, this is for a natural world, so a world without anthropogenic forcings. The orange distribution is for the world of today, so that's including both natural and anthropogenic simulations today. And then the red curve I also added because I was interested in looking at the future, and that's using mid-21st century conditions, so increased greenhouse gas concentrations. And if we compare those three distributions, we don't really see much change between them. And the dashed line here represents where 2016 is, and you can see that in the tail of the distribution there isn't much of a change either. However, if we look at comparing rainfall anomalies, winter rainfall anomalies for cool East Indian Ocean conditions in the current world in blue, and warm East Indian Ocean conditions in the current world in orange, we do see a shift in the distribution. So the orange curve is to the right of the blue curve, meaning that you're more likely to get more precipitation when we have warm East Indian Ocean conditions. And that carries through to the tail of the distribution as well. So the main conclusion of the study was that natural climate variability related to the warm conditions in the East Indian Ocean at least doubled the likelihood of this event occurring. The overall role of human-caused climate change in this event was minimal. This actually masks a more complicated influence on climate change because I'm not showing you the whole analysis I did here, but I find that human-forced climate change is increasing moisture content of the atmosphere during winter in Southeast Australia, but it's also reducing the incidence of circulation patterns that we would associate with rainfall. So it's kind of increasing the thermodynamic influence is increasing the probability of wet winters, but the dynamical influence is decreasing the probability, and they're kind of cancelling each other out. Whereas the East Indian Ocean warmth both increases the moisture content of the atmosphere in Southeast Australia and increases the incidence of low pressure systems in the region. So that's just running through a very quick example. But this is just one of many attribution studies. This is a map from Carbon Brief, which is a blogging site you might have heard of, and they've put together a map showing all the attribution studies that have been done over the last few years, peer-reviewed attribution studies. You can see by where the pins are, there's been lots in North America, in Western Europe, and in Australia as well, actually. For heat extremes, for example, Australia is the most studied region in the world. The different colours indicate whether there was a human influence found in a particular event, and the different symbols within those pins show the type of event that the studies were looking at. And we can see for Australia, there's lots of heat extremes being studied, as indicated by these thermometer symbols, rainfall extremes as well. And if you click the pins, you can learn more on individual studies. So this is just an example of a paper by Julie Arblaster from a few years ago. So there have been lots of attribution studies done to this point, but what's next for event? So this is just coming to the last part of the talk. So there'll be some questions at the end. But I think there's really 4 key areas that event attribution is going into in the next few years. Firstly, looking at attribution of the different physical processes behind extreme events. So as opposed to just looking at an extreme event, heat wave, we might want to decompose that in a bit more detail. So if we know, for example, heat waves in parts of Australia might have some forcing from the land surface, where low soil moisture might enhance the heat wave, we might want to decompose our attribution study to look at the influences of climate change and variability on both the low soil moisture leading up to the heat wave and other things associated with the heat wave, like a blocking high pattern, for example. And we can also try and decompose into dynamic and thermodynamic components, a bit like I did with the East Indian Ocean teleconnection with the record wet winter in 2016, as I was showing. Also, probably going to be a shift towards performing these studies for compound extreme events. Many of you might have seen the perspective, the nature climate change perspective on compound extremes that Andy Pittman was an author on recently. This is going to be more of a focus in general for climate science in the next few years. In terms of attribution and for events which are related to more than just one variable. So for example, tropical cyclones, you can look at various different variables with tropical cyclones, whether that's the precipitation they produce, the wind, the overall energy within the cyclone, or for droughts. We're not just interested in precipitation deficits, we're also interested in evapotranspiration and soil moisture. So these events are more complex than one variable, and we want to be able to understand how climate change and variability alter specific aspects of these events and how these come together as well. And this is a lot more difficult than looking at a single variable. Another area that event attribution is going towards already is kind of more impact relevant studies. So we've already done lots of studies looking at meteorological parameters like heat waves, so climate change influence on a heat wave or a heavy rainfall event. But we're also interested in the impacts of these events and how climate change has contributed to those impacts. So how many additional deaths were there due to a climate change enhanced heat wave? This was a question posed in a recent study in Europe led by Dan Mitchell, looking at the summer heat wave in 2003. And he found that you could attribute some of those additional deaths to climate change itself. Also, there's been a study looking at an extreme rainfall event in the UK from a couple of winters ago, looking at how many additional homes were flooded due to a climate change enhanced heavy rainfall event. And the original idea with event attribution, as kind of hypothesized by Miles Allen, who's a professor at Oxford University, was that we would use attribution studies to attribute blame for different climate change enhanced events and possibly eke out who should pay for the damages related with climate change enhanced extreme events. So this might be one way that event attribution studies might go further in the next few years. And another way might be towards operationalizing event attribution. We can already do rapid event attribution studies for simple extremes. So if we're interested in, say, a hot summer in Australia, we've already got the background of peer-reviewed studies and peer-reviewed methods to be able to do with models that we've already got the simulations for. So in theory, we could try and operationalize this process so that we regularly have event attribution statements after an extreme event for a simple variable. And this is something there's particular interest in Europe at the moment. And there's a big multi-million-dollar project called Euphemie, which is aiming to do this in a few years' time, have an operational event attribution system in place. So, I've just given a very, very brief overview of attribution in general, more focused on event attribution, but just touching on trend attribution as well. Both are useful in trying to understand the causes of a change in the climate system or the causes of specific extreme events. And this is something that people are inherently interested in. And I think scientists, as scientists as well, we're interested in going further into understanding the causes of the influences of climate change on individual processes within extreme weather events. So they serve quite a useful purpose. Trend attribution allows us to make those quantitative statements in the IPCC reports, looking at the roles of different forcings behind observed trends. So this could be the warming global and regional temperatures, and it also goes through precipitation changes as well. Event attribution allows us to try and estimate how much human-caused climate change or different modes of natural climate variability alter both the intensity and the likelihood of. This is an area that we've seen big expansion in the last 15 years or so. One of the key points I'm trying to make here is that before we actually conduct an event attribution study, there's quite a lot of considerations we have to make. Often, when there's an extreme weather event, we might get asked by different organizations if we can do a study looking at that extreme event. And often the answer has to be no, because we don't have either good enough observations or the right climate model simulations to look at that particular event. So it's not as simple as just identifying an extreme event and running our model simulations or using those model simulations and producing a number. It has to be carefully considered that we understand already the influences of climate change and variability on that class of extreme events before we can actually do an event attribution study. And what we're seeing at the moment and what we're likely to see in the next few years is that event attribution is advancing in quite a few different directions, both towards understand the meteorology and the climate change influence on the meteorology behind extreme events, but also in terms of understanding or producing useful impacts relevant statements on the influence of climate change and variability on numbers of casualties or costs to do with particular extreme events. This is just a list of references. Thanks. I'm happy to try and answer any questions if that works over the system.
Yeah. Thank you, Andrew. So we can open up the floor to questions for Andrew. You just need to use this microphone so that he can hear you. So if you're brave, come up, and then he can see you too, because he can see you through my laptop. If you're not brave and you want to just yell out your question, I can repeat it here. Questions for Andrew? Here we go. We've got questions coming, Andrew.
Hi, Andy. My question is, you said that there is a climate change fingerprint on the warming of the East Indian Ocean SSTs, and you said that the rainfall was connected to the East Indian Ocean SSTs. So how come you can't connect the anthropogenic fingerprint to the rainfall if there's this sort of indirect connection?
Mm-hmm. So the connection is partly through the fact that it's anomalously warm relative to other regions of the world. So whether the East Indian Ocean SSTs are higher than SSTs in the West Indian Ocean or in the West Pacific means that that basically dictates where the center of convection is in the tropics, and then whether you get a wave train to Southeast Australia. So it's not just the SSTs alone, it's kind of the anomalies in the SSTs, either anomalies in time kind of detrended or anomalies relative to other regions of the world. Does that make sense?
Yep, thank you.
Other questions for Andrew? Thomas, you can do it. Thomas is coming down the stairs.
Hi, Andrew.
Hi, Thomas.
Everyone loves hot extremes, but I think cold extremes tend to get a little bit neglected compared to hot extremes. So, because it's generally said that cold temperatures are decreasing faster than warm temperatures, does that mean that detection studies on cold extremes are easier, like as a signal-to-noise problem?
That's a good question. Probably in some parts of the world that would be true, but as you say, they kind of get neglected. So there's probably not been enough studies to clearly say that cold extremes are easier to, or a lack of cold extremes, or reduced frequency of cold extremes is easier to attribute to climate change than an increased frequency of hot extremes. But it would also be depending on the area of the world you're interested in. So for example, in parts of North America, we've seen a lot of cold extremes recently in winter, and people have been suggesting there might be a climate change increase in the frequency of cold extremes, but there's a lot of debate at the moment. So it varies depending on kind of changes in the dynamics as well of the weather patterns, as well as just the thermodynamics.
Andrew, do you want to comment on the Michael Gross Frost study?
Oh yes, so I think that was David.
That was David.
So yeah, Michael Gross's frost study. I can't remember the conclusion of that study, but he looked at frosts in southwest Western Australia last year, for 2016. But there've been a lot more studies on hot extremes and cold extremes, especially in Australia. I think that's the only study of cold extremes I can think of in Australia.
Certainly in terms of attribution, there's not...
In terms of attribution.
But what this one did show was that associated with the reduction in rainfall in wintertime over southwest Western Australia, there was a climate change signal in increasing the February price in wintertime in that specific region. Because there's also a climate change signal in the reduction in rainfall, clear skies, and temperatures over. So it's, how would I say, contrary to common expectations that there would be a reduction in cold extremes. This is in fact because of the complications for extreme cold temperatures, frosts, that clear skies can be very important, as we noticed last night in Canberra.
Yeah. So I could only partially hear that, but I think I got the gist of what David said. It's quite a good example of how the dynamical response to climate change also has an effect because of reductions in rainfall. We might get unexpected changes in cold extremes. It kind of also highlights the need for event attribution studies so that we don't just make guesses about the role of climate change, because as David said, I think that's kind of contrary to our first expectation of the effect of climate change.
You're going to project, Tony?
Yeah, I'll try and say louder. Andrew, you talked about some successful detection and attribution studies, but you also mentioned at the start that they can be miscommunicated. Do you have any examples of those kind of studies and any ideas or comment on why they went badly?
Yeah, so probably the main example was that there were several studies after a severe heat wave in Russia in 2010, which appeared to produce results that were conflicting. They weren't actually conflicting, it was more the way they were presented. And then was follow-up studies. It was a study led by Freddie Otto at Oxford, and she basically synthesized those different studies and showed that they didn't really disagree with each other. So it's quite important that when we do event attribution studies, we're very clear in the framing of the studies, and also that we work with journalists who might report on the study. When I've done studies myself, I've often found afterwards that if I read something that's been written up about the study in a newspaper website, for example, I would say it quite differently, and often they've kind of slightly misconstrued the results in some way. So I think it's important to work with journalists to make sure that the communication is as clear as possible to the public.
Any more questions? No? Okay. All right, let's thank you, Andrew, for dialing in.